людей.
Well, yeah, if she has to cancel, I'll try to have a different lecture. Is the recording on?
Good morning, everybody. Thanks for having me back. I think this lecture will be a little bit less dense than the last one, the diffusion capacity, so hopefully everyone likes that. You guys can see my slides okay?
Yep.
Perfect. So this first slide here is a picture of Adolf Eugene Fick, the famous Fick's principle. Very famous man. But it got me to thinking whenever I put this lecture together a few years ago, actually, was you never really hear the name Adolf anymore. And that's for obvious reasons. This man was born in 1829 and died in 1901. And I looked to see, you know, the popularity of the first name Adolf over time. And this graph shows which place in popularity. So if it was 1, it would be the most popular name. If it was 140, it'd be the 140th most popular name in Germany. And you can see over time on the bottom is 1890 all the way to 1950. And there was some steady decline, and then, you know, World War II and huge drop off here. So we really don't hear the name Adolf very much anymore. Maybe there will be similar changes, you know, with some other people who I won't talk about. Okay. So this is Adolf Fick. The agenda for today. So we're going to talk about what is VO2, which is the maximum oxygen consumption. What is VO2 max? We're going to review the Fick principle, a little bit about the historical evolution of the understanding, and talk about the two main theories of either a peripheral or central limitation for oxygen consumption in healthy people. And we'll describe the many inputs that can affect VO2 max and the disease states that can affect the VO2 max. We'll talk a little bit about endurance performance. And the references are listed throughout the lecture. And the primary reference is this one here, which I encourage people to look at if they are interested in reading in more detail. It's a very nice article. In this lecture, it's more interesting and fun in terms of day-to-day relevance to practice. Maybe not as much. It's more physiology, but it's fun. So the quick definition, so VO2 means volume of oxygen. If you put a dot on the top of the V, it means the rate. So this is then the rate of oxygen consumption. That's the VO2. And if you put VO2 max, that is the maximal rate of oxygen consumption. And so it's a very simple idea. You know, we use oxygen for aerobic metabolism. And what is the limit? What is the maximum amount of fuel we can burn? And that has, you know, implications for our exercise capacity, for what we're able to do. And it has implications in disease. If it's significantly lowered, then, you know, perhaps patients would not be fit for surgery, for example, or other things. So I talked about those two. Okay. The Fick principle of the famed Adolf Fick. So the oxygen consumption is very simply equal to the flow of blood multiplied by the difference in concentration between 2 points. And if you apply it to, you know, to the person as a whole, well, Q is just blood flow. And the 2 different points that you measure the change in oxygen is where it's highest and where it's lowest. So as it's leaving the heart in the arteries, that's the first concentration, which is the Ca here. And then when it returns to the heart and the mixed venous, that's the Cv here. So very simply, the amount of oxygen consumed is equal to the cardiac output, which is the blood flow, multiplied by how much oxygen do you have at the beginning, and then after your muscles are done extracting, how much oxygen do you have at the end? So very simple concept attributed to Dr. Fick, again, 1829 to 1901, so quite a while ago. And this Ca minus Cv we call the arterial venous oxygen difference. Now, in the 1920s, Hill et al. First described VO2 max and attempted to explain it. So this concept of maximal oxygen. And what they did is they took healthy people and they ran them around a track at different speeds and measured oxygen consumption. And at low speeds, the oxygen consumption went up as the speed went up. So I'll show you here this graph. And at low speeds, the oxygen consumption, which is on the y-axis, went up as the speed went up. But each of these lines represents one test subject. And you can see that the oxygen consumption plateaued. So no matter how fast they went or how hard they went, at some point, the oxygen consumption plateaued. And this was, direct evidence that each person had their own maximal limit of how much oxygen they can consume per minute. Okay. And here's another graph demonstrating the same thing. It's a little different experiment. So they took the same person and they told them to run at different speeds. And what you can see here is in this steep graph here, the steep line, they told them to run very fast. In this one here, they told them to run a little bit slower, and here a little bit slower, etc. And you can see that they get to the maximal oxygen consumption at different times, but the same subject has about the same oxygen consumption as long, once they get to a certain speed. And what they found was that, for this person, their maximum VO2, their maximum oxygen consumption was 4 liters per minute, beyond a speed of 243 meters per minute, which, for us is a 6-minute, 40-second mile. I'm not sure what that comes down to in minutes per kilometer, but I guess you could multiply that out here. So basically what they showed was that if you accelerate quickly or you accelerate slowly, eventually you will get to the same final maximum oxygen consumption. So back then, this was still a question: is there a maximal oxygen consumption? And the answer was yes. Okay. Next, so Dr. Hill and their group had a theory that there is a upper limit to oxygen uptake, and that individuals will have differences in how much oxygen they can consume, and that the oxygen uptake is limited by the ability of the cardiorespiratory system to transport oxygen to the muscles. So that was his theory, was that it's the cardiorespiratory system that is the rate limiting step. And remember, the pathway of oxygen, well, it comes from the atmosphere, and then it comes into the airways, into the lung alveoli, and then it has to diffuse across the capillaries to the blood, and then it has to bind to the hemoglobin, and then it has to circulate to the organs, and then it has to dissociate from the hemoglobin, diffuse through the capillaries, and get used by the mitochondria. So somewhere along this pathway, there's going to be a rate-limiting step to oxygen utilization. And at this time, it wasn't clear what that rate-limiting step was. And it turns out in healthy people, the rate-limiting step is going to be cardiac output. But in disease states, any of these things can limit oxygen consumption. So a reminder again, just to reiterate, the oxygen consumption is equal to the cardiac output multiplied by the difference in concentration of oxygen between the arterial side and the venous side. And so the oxygen consumption you can think of is limited by cardiac output or by the amount of oxygen that is contained in the arterial blood, which relates to the function of the lung, or by the amount that is extracted, which is then the venous concentration. Okay. Now, the oxygen content in the arterial blood is equal to the sum of two components. The vast majority is what is bound to hemoglobin, as you remember, and the number is 1.34 times the hemoglobin concentration. At least that's the way we do the units. It may be different if you have different units for hemoglobin than we use, multiplied by the saturation, plus this number, which is how much oxygen is dissolved in the blood. And this is usually fairly negligible. It's mainly this multiplier of the hemoglobin times the saturation times this constant. Okay. So we're going to start with looking at healthy people while they exercise. And this slide I really like. It's kind of a fun slide that shows you how much reserve you usually have. And on the top here is the alveolus, which is the end terminal unit of the lung. So in here, there is air that you breathe in with a partial pressure oxygen of around 100. And this red tube here is the capillary in the lung. And on the left side, blood comes in, and on the right side, blood leaves. So when the blood comes in, it is deoxygenated. The PO2 is low. And when the blood leaves, it is oxygenated. The PO2 is high. So what you'll see here is that as you progress along this gradient, there is diffusion that takes place across the membrane. And this diffusion normally only uses the first third or so of this actual interface. And that's demonstrated in another way by this graph, which on the y-axis shows the oxygen content of the blood. And as you progress from left to right, the oxygen content in the blood goes from 40 or so up to 100. And you'll see here that this has essentially equilibrated around a third of the way of this length here. So you have some extra leeway here, which is needed in certain circumstances. This is reserve. This is reserve from a diffusing perspective. But what happens to this curve as you exercise? So as you exercise, everything shifts a little bit to the right. And that's because your oxygen or your blood is pumped through faster, your cardiac output goes up. And so the blood spends less total time interacting with the alveolus. Okay? And so you could imagine that if you really exercise hard and you're somehow able to increase your cardiac output enormously, that you would potentially not equilibrate. You would potentially end at a PO2 of 60 or 55 or something. But does that really happen? Well, Dr. Hill observed that, and this was back, 1900s early, he observed that people didn't turn blue or become cyanotic with exercise. And so he thought, well, it's unlikely that in healthy people can make a cardiac output so significant that diffusion becomes a limiting factor. And it turns out that most of the time we have enough here where it isn't really a big effect. Okay. So what is the limiting factor? Well, Hill said, well, people don't turn blue when they exercise, so diffusion is probably not it, but maybe it's the cardiovascular system. And he observed that the maximal heart rate is fairly similar among age-matched humans. So we all know that, you know, the maximal heart rate is approximately 220 minus your age. So he thought probably the stroke volume is changing. And at the time, he saw on x-rays that, you know, endurance athletes had much bigger hearts than regular people. And he thought this kind of fits. Maybe it's just able to pump more blood per beat. And interestingly, though, another group, Powers and all, looked at trained athletes, so not just regular healthy people, but highly trained athletes. And as I showed you before, if you can make your cardiac output very, very high, then potentially diffusion would be a limiting factor. And it turns out that in an extremely well-trained athlete, it can make a measurable difference. So this group, they took these highly trained athletes and they measured the VO2 max on room air compared to 26% oxygen, so a few liters of oxygen. And the results are displayed here. So on the y-axis, we have the VO2 max, which is the maximal oxygen consumption. And on the x-axis, we have two groups. The first is the normal group, the control group. This is just healthy people like you and me. And you can see that if you had them on room air, which is this dotted one here, their VO2 max was some number. And if you added supplemental oxygen, their VO2 max change was negligible. Maybe a teensy bit higher, but negligible change. In the very highly trained athlete, so first off, on room air, their VO2 max was quite a bit higher than the healthy control, but the supplemental oxygen you give, even though they don't really desaturate that much, it does help. They are able to increase their VO2 max with supplemental oxygen. So it does cause a little bit of an increase there. Okay. I think I said all of that here, but I'll leave this so the translation is here. So the trained athletes when they were exercising, even though they didn't turn blue, their saturation dropped to 90%. So they still look nice and pink. But 90% is less than normal, 96, 97, 98. And if you give them supplemental oxygen, you can, you know, the difference between 90 and 96, 90 and 98 will increase their VO2 max a certain amount, which is what you see here. So basically, highly trained athlete, if you give them supplemental oxygen, they can increase their VO2 max and then also potentially their exercise, whereas regular person, no big changes. Okay, and the conclusion that he had from this was that if your cardiac output is strong enough, then diffusion can be a rate-limiting step, but usually it's not. Usually it's not. Okay, these are two famous athletes. This is Lance Armstrong, and I've included him here because he is a doper. He's now, he finally admitted to it after being caught, I don't know, 50 times, but obviously a famous Tour de France winner, cyclist, and he used some kind of designer erythropoietin to increase his red blood cell supply. And remember from that equation, a fixed equation, if you can increase the oxygen content in your arterial blood, you will increase cardiac output. And that's what he was doing, and I'm sure that helped him win. This guy had a more natural, this is Eero Montrayanta, and he had a more natural advantage. He had congenital polycythemia. So he had a mutation so that he had a high red blood cell count somewhat naturally. And he won distance skiing, 3 gold, 2 silver, 2 bronze. But what's funny about him is that that wasn't enough for him. He also doped, but he took amphetamines. So he had a natural advantage, and then he decided to also take amphetamines to help him win. So these are 2 famous blood dopers, basically. All right, so going back to the oxygen carrying capacity, this concept of blood doping, which was, adding blood to your circulation, from fixed principle is fairly clear. If you increase your arterial content of oxygen, because most of it depends on the amount of hemoglobin you have, then you should be able to increase your cardiac output. And this is fairly clear, and I'll talk through this experiment here, but basically, if you infuse a liter of blood or so, it can increase your maximum oxygen consumption 5 to 10%, somewhere in that range. So what you see here on the top screen here is your VO2 max, and what you'll see here in this 1350, for example, they have given this patient 1.3 liters of blood, and their VO2 max is significantly higher compared to if they gave the patient no additional blood. So it went from 5 liters per minute up to almost 5.5 liters per minute. And this is not surprising, but someone did the experiment, and so it's kind of nice to see. And animal models had very similar results, so they can do much more mean things for animals. So what they did was they took a dog's gastrocnemius muscle, and they changed the hemoglobin concentration, and they applied, current to make the muscle tense. And what they looked at was basically the consumption of oxygen in that muscle, which is on the y-axis here. On the x-axis is how much oxygen was delivered, and they changed that by changing the hemoglobin concentration. So as they increased the hemoglobin concentration, the amount of oxygen consumed increased fairly linearly. So at least on the dog hind leg, the dog gastrocnemius muscle, it had a very strong ability to increase consumption if it is supplied with more oxygen. And sorry, this is the same slide, but the canine muscle under maximum load with identical blood flow, and what they changed was just the hemoglobin concentration. And as you were able to increase oxygen delivery, the oxygen consumption was higher. So the muscle has a very strong ability to extract more oxygen, and it looks like, similar to the diffusion slide, there is a lot of reserve in muscle to use more oxygen. So it's hard for the muscle to not have it can always use more. Yeah. So we're then moving into the consumption, which is again in the muscles, mainly the skeletal muscles. So if the lungs can diffuse enough oxygen, and the heart can pump enough oxygen, and the blood can carry enough oxygen, will the tissue be able to use it all? And so this is again, this is now Fick's law, where you have the flow of gas is dependent on the change in partial pressure from one side to the other of a membrane, multiplied by the area of that membrane divided by the thickness. So this is, and we talked about this actually in the DLCO lecture, but this is basically, how gas will diffuse across a membrane. And obviously, if the area of the membrane is more, then it's easier to diffuse. If the pressure on one side is significantly higher on the other, then it's easier to diffuse. And if the membrane is very thick, it's more difficult to diffuse. And that's all that's kind of laid out here. This group, Honig et al., they looked at the extraction part of the physiology, and they used this canine hind leg muscle. And they saw that the oxygen drop is largest between the red blood cells and the sarcolemma in the muscle. And they found that if they increased blood flow to the muscle, in the absence of a change in the load or the work, then the oxygen extraction did not change. But unsurprisingly, if you increase the load on the muscle and the blood flow at the same time, then it will increase the oxygen extraction. And so it follows that you require to have a low partial pressure of oxygen in the muscle, and more accurately, you need a gradient between the blood and the muscle tissue. And that follows from the Fick's equation. It's fairly obvious, but they did the experiments to show it. So I say it's fairly obvious. It's fairly obvious now. Probably back in the early 1920s, 1930s, when they first did some of this stuff, it was not very obvious. So here's one example. They did a canine model where they held the load constant, and they gave them sodium cyanate. And sodium cyanate, if you remember, will change the affinity of hemoglobin for oxygen. It will cause hemoglobin to hold on to oxygen more tightly at any PO2. So on the x-axis is the partial pressure of oxygen. On the y-axis is the oxygen content of the hemoglobin. And the sodium cyanate is this left-shifted curve, meaning that at any PO2, it's more likely to hold on to oxygen if it's in the presence of sodium cyanate. Okay. So they did that, and then they looked at the blood flow and the oxygen delivery and the VO2, and unsurprisingly, the VO2, which is this third line here, the control group had around 12, and the group that was treated with sodium cyanate had around 10. And so, this diffusion can potentially be a limiting factor if you are left shifting your hemoglobin, oxyhemoglobin dissociation curve. Fairly straightforward and things that seem obvious to us now. Well, so we talked about muscle a little bit. Let's go deeper into the muscle and see, well, what about the mitochondria? How important are they in this limitation? And as we know, mitochondria use oxygen in the electron transport chain, and that drives down the PO2, and that's ultimately what permits diffusion into the muscle. And in 1977, this group, Saltine et al., they compared sedentary men and endurance runners, and I think they did actual muscle biopsies. And they showed that in endurance runners, the mitochondrial density increased by 2.2 times, so by 200%. But the VO2 max in those people only increased by 20 to 40%. So that raised some questions. So they have a lot more mitochondria than sedentary people, but their VO2 max didn't go up by 200%. And so they thought, well, probably it's not that. It's probably another reason for the mitochondrial density increasing so much. And even though I don't think his group showed it, but I'll at least answer that question here, is that it turns out that mitochondrial density is much, much, much more important in determining your endurance with submaximal exercise. So if you're not running at 100%, but you're running at 60, 70% for a long time, then the mitochondrial density is very, very important. So that's why it goes up by so much. All right, what is this one here? So they also looked at cardiac output and the arterial venous oxygen difference across skeletal muscle. And they showed that it can be actually pretty small if the blood is flowing through the muscle quickly without time to equilibrate. But it turns out that with exercise, your skeletal muscle has an enormous ability to increase the capillary bed, which slows the blood flow through the system. It increases the mean transit time. And what that does is it allows for more complete extraction of oxygen. And this is especially important at high cardiac output, where otherwise the blood would be moving too fast to take off all the oxygen. And that's demonstrated here. So on this side of the screen, we have the arterial side, which is red and oxygenated. On this side here, we have the venous side, which is blue and deoxygenated. And in the middle, we have the capillary bed, and the muscles are in here that are, diffusing. So what you'll notice is that there are a variety of sphincters here. And these are little muscles that will close off and prevent blood flow in this area. So with exercise, what happens is all of these sphincters open up and you get much more pathways for blood to flow from arterial to venous. And so even though the total flow of blood goes up significantly, the speed at which the red blood cell is moving through any one of these numerous pathways is now much slower. And so it allows for more complete extraction. So it turns out that in skeletal muscle, there is a huge ability to recruit more blood supply. And so, and the point of that is that you can then equilibrate the oxygen as it moves from arterial to venous. So again, the same group in 85, they measured oxygen uptake in the leg of a person going maximal exercise, and they compared it to the oxygen uptake in the leg when the whole body was going maximal exertion. And this is really actually the study that settled, where is the limitation? So as I've talked through the many slides before, I pointed out how you could have limitation in any one of the steps. And it wasn't clear exactly where the limitation was, if it's central from the heart and the lungs, or if it's peripheral with the body's ability to extract oxygen. And this is viewed as the main experiment that kind of settled things. So I'll lay it out again. They measured the oxygen uptake in the leg, which was going maximal exercise. And then in the separate case, they measured the oxygen uptake in the leg when the whole body was going maximal exercise. And what they found was if you just sit still and exercise your leg, it has a 2 to 3-fold higher oxygen consumption than if you're exercising your whole body at maximal. And very clearly from that, it showed that really the rate limiting step is supplying blood to the muscles. So the muscles have 2 to 3-fold higher ability to use oxygen than we give it in the normal healthy state. And from this, it was concluded that the rate limiting step in healthy people is usually cardiac output. And this is fairly obvious now, but this is kind of how it got to that state, how our understanding got to that state. Interestingly, what happens when people are deconditioned? So that means out of shape, or they're sitting in the hospital bed or whatever. This is a very small study, and it looked at people who are in bed rest, so like in the hospital, or they're sedentary, or they're training. And what they saw was that people who are sedentary have a cardiac output 1.5 times maximal of people who are in bed rest for a few weeks. And the people who are training, who are good athletes, have about twice as good cardiac output as those in bed rest. Oxygen consumption. And they looked into what is the difference between these three groups. And it turns out that when you're sedentary, the first thing that you lose is stroke volume, and therefore you lose a cardiac output here. When you're training, you can increase your stroke volume significantly, and that's this part here. But you can also, with training, increase the amount of oxygen you can extract, and that's the second part here. So if you're sedentary, if you're in bed rest, you are not efficient at using oxygen, and your heart is not very good at pumping it. And then if you go to sedentary, you can pump a little bit better. But if you're training, then you can really increase your oxygen consumption. So the overall conclusions in healthy people is that the limitation to maximal oxygen consumption is mainly on the supply side. It's a limit on the lungs' ability to supply oxygen to the blood's capacity to hold oxygen, and most importantly, the cardiovascular system's ability to pump the blood. That is the main limiting factor in healthy people. So it turns out we have way more lung than we need. We could always use more heart. All right. In general, though, every step in the transport and utilization of oxygen will contribute to the VO2 max, and each step has the potential to be the rate-limiting step under the right circumstances in the right disease process. And, for example, determinants of oxygen consumption could potentially include the oxygen content in the air, which translates to how much oxygen is in the alveoli, to the diffusion across the capillaries, to the hemoglobin's affinity for oxygen, the oxygen carrying capacity of the blood, the end organ PO2, the mitochondrial density and efficiency, the transit time through the capillaries, shunting in different disease states. So be aware that disease processes can affect all of these components, and that's kind of the main takeaway. But in health, the VO2 max is mainly determined by cardiac output. So before I mentioned that endurance performance does not strictly correlate with VO2 max. So VO2 max kind of sets an upper limit for performance. But if you do an endurance event like the marathon or something, they're not performed at VO2 max. They're performed at a certain percentage of VO2 max. And it turns out that the ability to maintain a percentage of VO2 max, they're much more important for runners with similar VO2 max values. And exercise efficiency is a very, very important factor in these top athletes. And mitochondrial density is also a very, very important factor. Now, this slide, this is a really cool article. I enjoy it. It's a New England Journal of Medicine article. It's a very brief one. And it talks about the high altitude adaptation. And this took place in Mount Everest. And what they did was they had 4 people, okay? And they went to Everest, to the top. And then as they came down, they measured, they drew blood at different places, and they checked the pH and the partial pressure of oxygen and partial pressure of carbon dioxide. And they found this pretty amazing numbers. So the pH for all 4 were on average 7.53. So they were alkalotic, which makes sense. I'm sure they were breathing quite fast. The oxygen, the PaO2, was between 19 and 30, which is extremely low. And it correlated to an oxygen saturation. So the first individual was satting 68%. The second was satting 34%. The third, 44%, and the fourth, 70%. So on average, it was 55% oxygen saturation, which is remarkable. And it's not just for somebody who's alive, it's somebody who's alive and walking up and down Mount Everest. More amazingly is the lactate concentration in the blood was about 2, which is not high. I mean, it's just borderline. So even though their oxygen saturation was so low, they are functioning with aerobic metabolism. They are not moving into anaerobic metabolism here, which makes sense because you can't really maintain anaerobic metabolism for that long if you're going to hike up and down Mount Everest. But even in this low oxygen state, they are able to extract oxygen and use it. How do they do it? Well, of course, they increase their hemoglobin significantly. So the hemoglobin is anywhere between 18 and 20, which is quite high. Upper limit of normal is usually, 14, 15. And then this respiratory exchange ratio, like the lactate, this also confirms that these patients or these subjects are not in anaerobic metabolism. So this ratio is less than 1. Okay. All right. So this slide shows a few things about how people adapt to high altitude. And this is again from the same paper, but this is now not the same people. And what we looked at in this slide is at different altitude, what happens to the oxygen content in the blood. So the first bar, the white bars, are the partial pressure of oxygen in the arteries. The light blue, or the kind of medium blue, is the saturation. The light blue is the hemoglobin concentration. And then the dark blue is the total oxygen content. And this is probably the most important, the total oxygen content. And on the x-axis here, we have the altitude. So there is a group of 10 people at 75 meters, a group of 9 people at 5,300 meters altitude, a group of 9 people at 6,400 meters altitude, 6 people at 7,100 meter altitude, and then the 4 people that are in this study at 8,400 meter altitude. So I'll first just go over the total arterial oxygen content. So from basically sea level, if you go to 5,300 meters, you can increase your oxygen content fairly significantly from here to here, even though your arterial saturation goes down a little bit, okay? So the total content goes up. And the reason it goes up is because the hemoglobin goes up fairly significantly. So the hemoglobin is this bar versus this bar. So this is adaptation to altitude. It turns out you can adapt even further. So at 6,400 meters, okay, even though the saturation, which is this dark blue here, is down compared to the previous two, you can still increase your hemoglobin more. So up, to the point where the total content, which is the really dark blue, has gone up again. So at 6,400 meters, the amount of oxygen you can carry in your blood is higher than at 75 meters. Okay? Now, this seems to be about the peak, though. As you get even higher than that, the hemoglobin increase does not make up for the fact that the saturation goes down, 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 down. So what you end with here is that as you go higher, your arterial oxygen content goes down, and then at 8,400 meters, now your arterial oxygen content is quite a bit less than what it is at sea level. But interestingly, at 7,100 meters, it's about the same. Okay? So with adaptation, your body can run about the same oxygen-wise at 7,000 meters above sea level compared to basically sea level. That's what they demonstrated here. It's just kind of neat. I don't know. I find these extreme physiology pretty interesting. All right, so some examples. So the VO2 will, of course, change if the cardiac output, the arterial content of blood, venous content of blood, or some combination will change. For example, if you have heart failure, you will have reduced cardiac output. If you're on beta blockers, you will decrease the cardiac output by decreasing the heart rate. If you have pneumonia, for example, you will decrease the arterial oxygen content because you have VQ mismatch. In COPD, you will decrease the arterial oxygen content and decrease the cardiac output in advanced cases. In interstitial lung disease, you will decrease the arterial oxygen concentration, mainly through VQ mismatch and diffusion problems, and you will also decrease cardiac output with concomitant pulmonary hypertension. With anemia, of course, you will decrease the arterial oxygen content. If you're at high altitude, you will decrease the arterial oxygen content. If you have various mitochondrial diseases, you will increase the venous oxygen content because it is not extracted. If you have cyanide poisoning, for example, you will increase the venous oxygen content because it will not be used. And this is a bonus slide, but I also thought this is kind of fun. So this is the VO2 max by species. And what we look at here is on the x-axis is the body mass index, and then on the y-axis is the oxygen consumption. And the general trend is that as species gets bigger, the oxygen consumption goes down, but some species are able to extract more for their size, and some are able to extract less for their size. And man is right here. We're a little bit worse than the average line would predict. We're a little bit worse than this is lion. This is a goat. Horse over here is pretty good, it turns out, but not as good as dog. Dog is quite good for its size at extracting oxygen. But yeah, so these are the different species in this line here. And I think that's all I have. Hopefully that was enjoyable. I don't know how relevant, but it's kind of interesting stuff.
Adam, thank you for your lecture. It's, of course, most basic, yes, not clinical lecture.
Yes.
So this type of lectures, скажем, require less questions in first period. But
Sure.
if I have question, you told about mitochondrial diseases that some pathological states, yes, that lead to changes in oxygen consumption, yes, and maximal volume, no, maximum VO2. What did you mean as for mitochondrial diseases?
There are a few that are inherited. I'm trying to remember the names of them now, but they come up. So we do cardiopulmonary exercise testing in our pulmonary function lab, and there are a few patterns that are suspicious for mitochondrial diseases. And honestly, off the top of my head, I don't remember the names of a few of them, but there are a few X-linked diseases that surprisingly don't have too much other manifestations than, decreased maximal oxygen consumption. And they tend to have an early lactate threshold and just a poor exercise capacity. Very serious ones don't make it. I mean, very serious mitochondrial diseases, I don't think make it through pregnancy. But there are various degrees of mitochondrial efficiency. And there are some patients that have evidence that they have, mitochondrial limitation. And you can see it in exercise. I remember I have one patient that had this pattern on cardiopulmonary exercise testing. But I admit I would have to look it up. It's not something common at all.
Thank you.
Sure.
Colleagues, maybe some questions? Okay, and more question. How endocrinology diseases affect on consumption of oxygen, yes, and maximum VO2.
I think it's mainly through cardiac output. Like hypothyroidism, I think is going to be mainly through cardiac output, for the most part. Because unless you're really affecting all of these things are possible, but usually it's something is affecting cardiac output negatively, and that is what's causing the issue, or something, or anemia, of course, is affecting arterial content of oxygen, or very bad lung disease causes VQ mismatch, and then you're not able to diffuse properly. But most of the time, we blame the heart. But as pulmonologists, we like to blame the heart. So.
Okay, thank you. And the last one,
Sure.
as for, according to our lecture topic, yes, my question is not about this topic, but hyperbaric oxygenation.
Yes.
So what is your meaning about hyperbaric oxygenation based on these physiological dates?
Oh, I mean, so hyperbaric oxygenation, of course, is where you put people in a chamber where you can increase the pressure and therefore increase the dissolved oxygen content in the blood. And it's an interesting thing, does it matter? Well, that is debatable. So it's done sometimes for burn patients. There's few cases where people do it. In theory, you can increase the oxygen dissolved in the blood so much that the hemoglobin doesn't even need, you can measure the arterial oxygen saturation and the venous oxygen saturation, and there isn't much difference. So you can dissolve so much in there. The theory behind it is just that somehow it would diffuse better from dissolved content in the blood to whatever tissue it's going to. I have a hard time believing that it makes much difference because, where the blood goes, the hemoglobin goes. And so this concept that if you do hyperbaric oxygen, it may increase healing or whatever, I don't think data has shown robustly that actually happens. But I mean, physiologically, obviously what happens is you increase the pressure so you can dissolve more oxygen in the blood, and then ideally it will dissolve out of the blood into the areas that get less blood supply, and then maybe you have more oxygen available for consumption for healing. But most of the time, delivery of oxygen is not the problem. In these areas, there is enough capillary bed and whatever. So it's, I think, a controversial area. Some people may argue differently than I would on that, but yeah. Yeah. All right. Well, thank you very much.
Yes, thank you very much, Adam. It was interesting and helpful. Thank you. It's a good topic of the base of education. Thank you.
Yeah, physiology. Thank you. Bye-bye.
Да. Bye-bye. Колеги, ну що, ми прощаємось до наступного четверга, так? Як завжди, о 15:00. Всім дякую за участь. Наступного разу все ж таки запитую